Hello, everybody. My name is River Robles. I'm a PhD student at Stanford University, but I do all my research at SLAC National Accelerator Laboratory, where I do research and development into X-ray free electron lasers. And today I want to talk to you about synchrotrons and X-ray free electron lasers, how they work, what they can do, and where they're headed. So the context for this is that at SLAC National Accelerator Laboratory, we have three different accelerator-driven X-ray sources, one device called a synchrotron and two devices called X-ray free electron lasers. In this aerial view of SLAC, you can see here, they are these three things that I've circled. We have a synchrotron called the Stanford Synchrotron Radiation Light Source, and two free electron lasers, both of whose names start with LCLS, or LINAC Coherent Light Source. And the goal today is that by the end of the talk, you'll understand the basic physics of how these devices work and what makes them different from each other. So if we take slightly higher quality aerial images of these devices, you'll see them here. On the left, you see SSRL, the synchrotron device. Synchrotrons are X-ray sources that are fundamentally circular in nature. They're driven by a circular accelerator. And on the right, you see the LINAC coherent light source, a free electron laser, which is a linear accelerator. And these look very different from the sky. If we sort of cartoonize them and try to understand what are the basic ingredients to making a synchrotron or a free electron laser, you'll see that they're not actually so different. When we look at a synchrotron, the basic component is this circle that keeps a high energy electron bunch moving at nearly the speed of light. We call this very creatively the storage ring. And every once in a while throughout that ring, the electrons will go through what we call insertion devices, which are often what these things we call undulator magnets. And it's at these undulator magnets that the electrons are prompted to make radiation, generally in the form of X-rays. And if you compare that then to a free electron laser, you'll find that the picture is really not so different in the sense that you still have some accelerator generating a high energy bunch of electrons moving very close to the speed of light. And at the end of that accelerator, the electrons are sent again into an undulator magnet. So to understand how synchrotrons and free electron lasers work, we need to understand how electrons behave inside of these things called undulator magnets and what those undulator magnets are in the first place. They look like this in reality. On the left, we show a prototype of the LCLS undulators. And on the right, I show a segment from the LCLS2 undulators. You can see that it's basically made up of these rows of magnets, where basically what we're forming is a set of dipole magnets, where as we move from one set of dipole magnets to the next, the polarity changes so that the first pair of magnets here will push an electron beam in some way. The second pair pushes that beam in the other direction. And then we go back and do it again with a third, and so on. And we periodically move the beam back and forth in these dipole magnets. If we cartoonize that, it looks something like this, where we have, as I said before, this first pair of magnets forms a dipole with some polarity. The second pair forms a dipole of the opposite polarity. As we move along, we do this periodically so that we form some magnetic field, where the peak of the magnetic field is about a Tesla. The shape is sinusoidal, and the period of that sine wave is typically a few centimeters in undulator magnets used at synchrotrons and free electron lasers. And the last ingredient is this electron that we send in with some velocity very close to the speed of light. I'll remind you or tell you that in special relativity, that velocity corresponds to some Lorentz factor, gamma, and special relativity is going to come up a lot as we talk about how these devices work. And as this electron moves into the undulator, it will similarly be sent on some wiggly trajectory, wiggling back and forth as it moves through the undulator. And the key thing to remember now to understand why we end up making X-rays with this is that when you accelerate a charged particle and taking it and moving it on a wiggling trajectory is accelerating it, that charged particle gets prompted to emit radiation. And now I want to try to explain to you why we can wiggle this electron with this few centimeter period in the undulator and end up making X-rays with angstrom and nanometer wavelengths. And to do that, I actually find it easier to move from this picture we've had so far, which was in the lab frame, which is of an electron moving towards some undulator with some centimeter scale period, to a picture in the rest frame of the electrons. in which the electron is initially sitting at rest, and now this giant undulator flies towards it. And as the undulator flies over the electron is made to wiggle up and down, basically sitting at rest longitudinally, but wiggling up and down transversely. And an electron wiggling up and down like this, you can think of as an electric dipole that's oscillating. And an oscillating electric dipole emits something called dipole radiation. In particular, if I have an electric dipole that oscillates with some frequency, it emits radiation with the same frequency. So how does that then imply that we make X-rays when we send an electron through the undulator? Well, the basic picture you can think of in 3 steps. You have an electron which enters this undulator field, which has a period of lambda u in what we'll call the lab frame, basically, R frame. When we move into the rest frame of the electrons perceive the undulator as being length contracted by special relativity. And it sees an undulator field with a period which is gamma times smaller than it was in the lab frame. And in particular, because this electron is moving very close to the speed of light, this Lorentz factor can be very large. At accelerators today, it is typically from a few thousand up to a few tens of thousands. And as the electron sees that field, it oscillates up and down like an electric dipole, and it emits dipole radiation with that same contracted wavelength of lambda u over gamma. Of course, we are not living in the rest frame observing this radiation. We are observing this radiation in the lab frame. So we have to think about what changes now when we sit at the end of the undulator and watch this radiation coming out of the electron. Well, we perceive it with another effectively length contraction of the wavelength thanks to special relativity. And now back in the lab frame, the radiation emitted by the electron does not have a wavelength of undulator period divided by Lorentz factor. It now has a period of undulator period divided by Lorentz factor squared. And this is super powerful because now we can take centimeter scale undulator magnets and divide them by this gamma squared factor, where gamma can be on the order of 10,000 in modern accelerators. And you quickly find yourself at the angstrom and nanometer level that you want to be at for X-rays. And I like to point out that though we've used this special relativity argument to get here, this is not really any different from the typical Doppler effect that you will perceive when you hear an ambulance driving by you and you hear its siren at a higher pitch when it's driving towards you than if it were at rest. It's the same basic concept that this electron in its rest frame is sitting there oscillating up and down, emitting radiation, and we perceive that radiation with some relativistic Doppler shift that pushes it from the centimeter scale to the X-ray scale. Now, that radiation emitted by an electron in an undulator is what we call undulator radiation. And I want to talk a little bit more specifically about some of its characteristics now. It has some central frequency or central wavelength given by this formula. When you do a slightly more careful calculation, you get this undulator period divided by gamma squared. You also have a factor of 2. And then you have this correction that is because of the strength of the undulator field. So we write it in terms of this normalized parameter K, which is proportional to the undulator field strength. And for typical magnets with centimeter scale periods and Tesla scale fields, K is usually between 1 and 10. The bandwidth of the radiation that gets emitted, it is about 1 over the number of undulator periods that the electron goes through. And the angular spread of the radiation is 1 over this Lorentz factor times the square root of the number of undulator periods the electron goes through. And this is basically how synchrotrons work. They operate on this principle of undulator radiation. And one of the most exciting things about it, besides the fact that it allows us to get to the X-ray regime, is that the radiation wavelength is extremely tunable in a way that it is not true of, say, conventional laser sources. The radiation wavelength, like I said, can be written using this formula, where the undulator period is typically a few centimeters. The Lorentz factor is typically around 10,000. Like I said, anywhere from a few thousand to a few tens of thousands. And this undulator K is typically around 1. And the really powerful thing is that by changing any of these 3 parameters, we can change the radiation wavelength. And in particular, changing the beam energy gamma and the undulator strength K are relatively easy to do, either by changing the energy of the accelerator or by physically changing the distance between the faces of the undulator. So as an example, I'll take the LCLS2 soft X-ray undulators, which have a period of 3.9 centimeters, a Lorentz factor for the electron beam, which these days operates around 7,000, and a K, which can be varied from 0 to 5.5. And you'll find from this plot that by varying K over its whole range, we access roughly an order of magnitude in radiation wavelengths from about 0.5 nanometer to a few nanometers. So that sort of sums up what I want you to understand about synchrotrons and undulator radiation. Now I want to answer the question, what exactly is different between a synchrotron and a free electron laser? And it turns out that the key thing that we need to understand in order to get from synchrotrons to free electron lasers is interference, right? If I have a bunch of electrons emitting their individual waves of X-rays, in a synchrotron, you have an electron bunch that is very long compared to the radiation wavelength, and the electrons in that bunch are organized randomly, right? They have no relationship to the radiation wavelength. They're just organized randomly within this very long bunch. And correspondingly, when I add up the individual waves from each of these electrons into the total wave emitted by the beam, I will get not quite constructive interference, not quite destructive interference, but something in between, where the amplitude of that total wave they emit scales like the square root of the number of electrons emitting radiation. That means also that the power grows linearly with the number of electrons emitting radiation. And so basically, you can understand it as the sum of a bunch of waves with about the same amplitude, but random phases. And the number of electrons in electron bunches in modern accelerators is usually anywhere from 1 million to 1 billion. So you get quite a bit of juice by adding up the waves in this way. But what you'd really like to do is to have a picture like this, where if we could somehow organize the electrons in the beam on the scale of the radiation wavelength, we could get it such that their waves would constructively interfere with each other perfectly, leading to a total wave whose amplitude grows linearly with the number of electrons, and power which grows quadratically with the number of electrons. And this becomes a way to get many, many orders of magnitude more X-ray power than you could get from the synchrotron with the spontaneous undulator radiation. The question then, of course, is how do you do that, right? We'd like to get to some situation in which we take our relatively long electron bunch and make the electrons in that bunch group themselves into little packets separated by the radiation wavelength. And when the bunch has this shape, we call this bunching. Now, of course, this is not easy to do because if you want to impose this structure on the beam with the period that is the radiation wavelength, it implies you had some force that was able to push them together like this that had the period of the radiation wavelength. Of course, we're building the free electron laser and the synchrotron to make X-rays because we don't have such a source of, say, an X-ray field with a period in the angstrom and nanometer scale that could do this kind of thing to the electrons. So how do we end up making the beam into this shape? Well, it turns out amazingly that the beam will do it to itself if you give it enough time and if the beam has enough high enough quality, which I don't have enough time to really explain what that means, but we'll just take it with a grain of salt for now. But it turns out that we have something called the free electron laser instability, which can take place. And that instability goes something like this. At the beginning of a free electron laser, the electrons are randomly distributed, like I said before. Their individual waves add up, not perfectly constructively, not perfectly destructively, but somewhere in between. And we get some weak total X-ray field emitted by the electrons. Now, the key thing to notice is that the electrons don't just emit this radiation, and that's the end of the story. They still see the effects of that radiation. They interact with it and feel forces from it. And what those forces will do is, for example, in this picture, if I'm this electron sitting near the top of this wave, I would get pushed backwards. And if I'm this electron sitting at the bottom of the wave, I'll get pushed forwards. And so in general, the electrons get pushed towards these positive zero crossings of the wave. So in a bit of time, after the electrons have some time to respond to that force and move, they get a little bit closer to each other. They get a little bit more bunched. As a result, their waves add a little bit more constructively, and the total wave gets stronger. But this just pushes them closer to each other along those zero crossings. And by the end of a free electron laser, we can get to a situation where we actually do achieve this bunch state, where the electrons gather into these packets that are separated by roughly one radiation wavelength, and the total wave emitted by those electrons is the constructive interference from all of the individual waves. This is called the FEL instability, and at its core, it's this feedback loop of we make a little bit of radiation, that little bit of radiation enacts forces on the electrons respond to those forces and move closer to each other, which makes them emit even more radiation, and so on. And we go on and on until we reach this fully bunched state. And if we look at how the radiation power evolves through the undulator, you get something like this. We're plotting the power here on a logarithmic scale. And what you'll notice is that as the bunch develops this micro bunching, the radiation power grows linearly on this log scale, which means in a linear scale, it grows exponentially. So we get exponential growth of the radiation power along the length of the undulator. And eventually, when we reach this fully bunched state, that radiation exponential growth saturates, and we reach what's called saturation. So that growth in the exponential gain regime has some gain length, we call it, which is typically a few meters for modern free electron lasers. And that saturation point typically happens about 20 gain lengths into the process. And so you can combine these two facts to realize that undulators for free electron lasers are typically around 100 meters long, which is why they have to be built in these long linear arrays rather than in this big circle like the synchrotron. Now, one of the before I move on, I want to say this is the fundamental difference between a synchrotron and a free electron laser, is that in a synchrotron, we have the initial organization of the bunch, which is random. They're not distributed in any particular way with respect to the radiation wavelength. And as a result, they emit this not perfectly constructive, not perfectly destructive total wave that with a power that scales like the number of electrons. When you get to this point where the beam is able to act back on itself through the radiation and form bunching, go through this exponential gain process, and get quadratic growth of the power with the number of electrons, you reach the free electron laser regime of this process. But at the end of the day, it's all electrons moving in undulators emitting X-rays. But a really interesting feature of X-ray free electron lasers is the way that we start up this instability, this feedback loop. As I said at the beginning of this, at the beginning, you have some electrons which are distributed randomly and they emit some relatively weak total wave. And that total wave that they initially emit starts this feedback and this exponential growth process. You could imagine a different world in which if we had some strong X-ray field from somewhere else and we used that to start this process, we might have a little bit more control over what's going on. But we're building the X-ray free electron laser because we don't have such a source of X-rays. And so generally, X-ray free electron lasers start from the random noise in the bunch like this. And when they do, we call it self-amplified spontaneous emission, or SASE. This means we are amplifying our own spontaneous emission from the beginning of the undulator. And this has really interesting ramifications for the temporal structure of a SASE FEL. In particular, the random noise in the bunch at the beginning of the bunch, at the head of the bunch, knows nothing about the random noise at the end of the bunch or in the middle of the bunch or anywhere else for that matter. And so if you look at the temporal structure of undulator radiation, you'll get this X-ray pulse, which is about as long as the electron bunch, but is composed of these very many random uncorrelated spikes. As we move through the undulator, these spikes get longer thanks to an effect called slippage that I don't have much time to talk about. But by the end of the undulator, when you reach the saturation regime, you'll still have an X-ray pulse, which is about as long as the electron bunch. Now with these random uncorrelated spikes, they may have gotten a little bit longer, but they're still random and uncorrelated. And as a result, SASE FELs are what we call not longitudinally coherent. It turns out they have transverse coherence, but they are longitudinally incoherent. And if you look at the spectrum of the radiation, you'll see a similar story where we have some total bandwidth dictated by the FEL instability, but it's broken up into these uncorrelated random spikes. So a lot of the research and development that goes into X-ray free electron lasers, in particular SASE FELs, is about how to improve the longitudinal coherence, to take this many spiked structure and turn it into a single spiked structure. And there are sort of two ways you can envision doing that. One is to generate a very narrow single spike in the spectrum. That would correspond to a very long single spike in the time domain. And we have one of the most popular ways to do this these days, which I don't have much time to talk about in this talk, is something called self-seeding. And in self-seeding, we can basically disrupt the FEL process halfway through the undulators, clean up the spectrum at that point, and then amplify that cleaned up spectrum. And when we do that, you'll get measured spectra like I show here, where you take this noisy, very broad SASE spectrum and turn it into this roughly single spike, very narrow seeded spectrum. We have similar ways we plan to do this in something called the cavity-based FEL, in which we take the free electron laser and wrap it with some optical cavity that can recirculate the X-rays. That turns out to also be able to get you single spike, very narrow bandwidth radiation with very high average power. And on the other side of longitudinally coherent SASE FELs, you have what we call single spike attosecond FELs. And in this case, instead of making a narrow single spike in this frequency domain, we make a narrow single spike in the time domain, corresponding to a very broad single spike in the frequency domain. And these are actually some reconstructed experimental pulses from the LCLS, where you can see that we generate pulses with few hundred attosecond durations and roughly single spike structure that are ideal for studying very ultra-fast processes. So before I wrap up this talk, I want to go back to the two free electron lasers we have at SLAC and tell you about the differences between them. They're the LCLS2 and the LCLS. And starting with the LCLS, this is a normal conducting copper accelerator, which reaches about 14 GeV electron beam energy. It's actually the first X-ray free electron laser in the world. It was the first device to demonstrate the FEL instability in the X-ray regime. It has 120 hertz repetition rate, and it's mostly used for hard X-rays nowadays. And that's because of our new accelerator, the LCLS2, which is a superconducting accelerator, which reaches 4 GeV beam energy, that eventually will reach 8 GeV beam energy after our high energy upgrade, or HE upgrade. And the most exciting thing about it is that because it's superconducting, we can operate it at much higher repetition rates, ultimately up to 1 megahertz. So for now, because of the lower beam energy, this is a soft X-ray machine. But with the eventual HE upgrade, we'll reach hard X-rays with megahertz repetition rates. So I want to wrap up by putting our X-ray sources at SLAC sort of in context. We like to do that with this plot of peak X-ray brightness on the y-axis and average X-ray brightness on the x-axis. On the bottom left here, you have synchrotrons like SSRL. These, as you can see from the plot, make comparatively small X-ray brightness compared to free electron lasers. But their power is in the fact that because they are circular and they don't require very long undulators, you can have a lot of X-ray sources distributed along the length of the circumference of the synchrotron. As a result, you can deliver X-rays to a lot of users at once. So SSRL and synchrotrons more broadly are workhorse machines that allow you to do a lot of science at the same time. As you move up the y-axis about 10 orders of magnitude in peak X-ray brightness, you get to the LCLS and X-ray free electron lasers, where because you have to operate in a line, because you have to give the electrons time to undergo this FEL instability, it's much harder to serve a lot of users at once. Currently at the LCLS, we can serve 1, 2, sometimes 3 users at once, but no more than that. But what you gain from paying that cost is much higher X-ray intensities, 10 orders of magnitude in X-ray brightness, and the ability to generate very short pulses from the 100 femtosecond range to the 100 attosecond range. And now to get to the LCLS2, we move 4 orders of magnitude over in average X-ray brightness, where we can do basically everything the LCLS could do, but now 10,000 times more times per second because of our megahertz repetition rate, allowing us to do about 10,000 times more science per second. And that is just about all I had to say today. I hope that you have learned something from this. I hope that it's been interesting. And I hope that if you find yourself doing research at SLAC, in the near future, in the distant future, I hope that it's successful and fruitful. And thank you so much for your time.